I'm Ava.
And I'm Beth.
This is Calculus AB.
Are you ready to graph this function? I am. Differentiable means able to take the derivative of. In order for a function to be differentiable, it must be continuous, which means the limit as x approaches a, f of x equals f of a. However, not all continuous functions are differentiable. So for the first function, f of x equals the absolute value of x. Now, it is continuous, as you can see by the graph. However, when you take the derivative of it, as x approaches a, f of x does not approach the same value from the left and right, therefore it's not differentiable. This is at the origin x equals 0. On the second graph, there's a vertical tangent, so this doesn't make it differentiable because you can't take the derivative of a tangent. And for the third graph, it is differentiable. And if it's differentiable, that means it's continuous. So now you might be asking yourself, well, how did you know that? Well, we have the equation g of x equals x squared. Now, as you can see, it's a continuous function. And you can do this by testing points. So the limit as x approaches 1 of f of x equals f of 1, etc. You can test this for all the points, and you're going to get the same thing true. The limit as x approaches a, where a is just an x value, f of x equals f of a. And then when you take the derivative of this function, you get 2x. And 2x is just a line that is continuous and continues on forever. And you can take the derivative at every point because there's no vertical tangent and there's no corner-like shape.
This function is not continuous because this is another one of those jumped discontinuities where the left side there's a graph with an open circle, and then going towards the right side is a graph with a closed circle, and that doesn't work. It's not continuous, so it's pretty easy. Since it's not continuous, we know that it is definitely not differentiable.
Mean value theorem, which is always called MVT normally. A function is continuous over the closed interval AB and differentiable over the open interval AB. Then there exists an x where f prime of x equals f of b minus f of a divided by b minus a. All this is basically saying is the slope of the tangent line equals the slope of the secant line if the function is differentiable and continuous. Mean value theorem examples. So we have the equation y equals x squared on the closed interval -2, 4. Does MVT apply? If so, find f prime of c. So we know that this function is continuous because it's a polynomial. And we know it's differentiable, as we've seen in the last example. So we use MVT, and we do f of 4 minus f of -2 divided by 4 minus -2, which is 16 minus 4 over 6 equals 2. What? How did you get f of 4? How did you get f of -2? How did you even get those y values? Well, you plug them into x squared. F of 4 equals 4 squared, which equals 16. F of -2 equals -2 squared, but the -2 is in parentheses, so it becomes 4. Hopefully that makes sense now. So earlier in this video, we talked about how absolute value equations are continuous but not differentiable. So I like to say no. And that means MVT does not apply. So we don't have enough information to find f prime of c. Extreme value theorem. Where is the absolute min or max? Make sure to check all endpoints and critical points. So we have method 1. Look at y values when f prime equals 0 or is undefined. So we have an example here where f of x equals 2x squared minus 4x plus 7 on the closed interval 0, 4. So first things first, we take the derivative. If you don't know how to take the derivative, we're going to link the video above. And then once we have the derivative, we set it equal to 0. This lets you find the critical point. So once we do that, we do some algebra and we get x to equal 1. Then we make a line chart and we make sure to test the endpoints on our line chart. 0 and 4 are the start and the end of the closed interval. The line chart is just that line with the arrow on it. However, there shouldn't be arrows on it because it's on a closed interval. Anyways, we plug in a number in between 0 and 1, let's say 1/2, into the derivative, and you get out a negative number. That tells you that all the numbers in between 0 and 1 are going to be negative. You use the same strategy for 1 and 4, finding out if it is negative or positive. So you plug in any value in between 1 and 4, so let's arbitrarily pick 2. So we will plug in 2 into the derivative, and we find out that it is positive. This tells you that all the values in between 1 and 4 are positive. And again, make sure they include the endpoints. Then we know that 1, since it goes from negative to positive, is a critical point because f of x changes direction. Next, we make a table to find the absolute max and min. We go in and we plug it into the original function. So we plug in x equals 0 to get out 7, x equals 1 to get out 5, and then x equals 4 to get 23. We find that actually the absolute min is 1, 5, the absolute max is 4, 23. So there's a second method where you graph the functions. So we have the same equation, we just graph this function, and we can tell by the graph where the absolute min and max are for this function. The absolute max will be the highest point on the graph, so the highest y value, and the absolute min would be the lowest y value on the graph, or the lowest point. We're doing the first derivative test. This is a very important rule to know. For the first derivative test, you take the derivative of the function, and if f of x goes from negative to positive at an x value, then there's a local minimum at that x value. Basically what this says is, let's say f prime of x goes from negative to positive at x equals 2. Then there's a local minimum at that x value, at 2. If f prime of x goes from positive to negative at an x value, there's a local maximum at that x value. If the function doesn't change signs, then there's no local minimum or maximum. According to the first derivative test, it fails in this case. So let's try a problem. This is kind of confusing and complex and it takes some practice. The problem says find the local minimum of g of x when g of x equals 4x squared plus 4x plus 1. And we need to make sure that it's a local minimum by testing values. And in order to do this, I recommend making a line chart as I did. So we're going to take the derivative. If you don't know how to take the derivative of a function, please check out the derivative video, which is linked in the description below, and it's going to appear in the corner of your screen too. And we get the derivative to be 8x plus 4. We set this g prime of x equal to 0, and then we factor out a 4 as I showed below, and we get that x equals negative 1/2. Now, it's really, really important to test the value to make sure it's a local minimum, because sometimes these problems like to trip you up, and there may never be a local minimum there. So I tested a value less than negative 1/2. You can test any value less than negative 1/2 in this case. I tested negative 2, so I plugged in negative 2 into the derivative g of x. So I did 8 times negative 2, which is negative 16, plus 4, which is negative 12. And I get a negative value when I plug in negative 2 because I had negative 12. And then when I plug in, let's say 2, that's a positive value. So 8 times 2 is 16. 16 plus 4 is 20. I get a positive value. So this is indeed a local minimum. How do I know this? Because g prime of x goes from negative to positive at x equals negative 1/2.
Time to apply your knowledge. So here we have this equation, g of x, and I'm asking you, at what values does the graph of the function g of x have horizontal tangent lines? Give it a go. What you have to know for this problem is that when a line is horizontal, its slope equals 0. And as we know, derivative is synonymous with slope, so we just have to set the derivative equal to 0 and solve for x. And once you do that, you'll get the x values of 0 and -2. Normally the problem would specify if they're asking for the x values or the y values. I just put the x values there, but if you wanted to be extra careful, you could plug them into the original equation to get your y values as well. We've done problems like this in the past, so hopefully this is familiar territory for you. Okay, cool. So we need to use point slope here because we're finding the equation of a line. And in order to use point slope, we need an x coordinate and a slope. So we already have that x value. It's x equals 2. It was given in the question. So I plugged 2 in for x in the original equation and got 2 as our y value. So now we have our full coordinate, 2, 2. And next we need to find the slope of the tangent line, which is the same thing as y prime of 2. So you have to find the derivative. And you need to use quotient rule. Hopefully you know how to do that by now. I get 3 over x plus 1 squared as y prime, our derivative equation. And now we just need to plug in that x value of 2, and we get 1/3 as our slope. Now we put it all together using point slope equation, and we get y minus 2 equals 1/3 x minus 2. And that is the equation of our tangent line. We are stepping into the realm of implicit differentiation. So what that means is we are taking the derivative of something that has 2 variables in it. There's both an x and a y. And that trips people up sometimes. You have to do it a little differently. It's not just a y equals blah 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 equation. This is an equation of a circle. You could have an equation of an ellipse or a certain kind of parabola. Here we have x squared plus y squared equals 1. When you're doing implicit differentiation, you have to take things in terms of dy dx, which you'll understand in just a minute. So you can take the derivative of x squared like you always do. It's just going to be 2x. Since it's the derivative of x in terms of dy dx, you just get 1, as I sort of show here, because the x's cancel out. So you just take the derivative normally for x. There's nothing else you have to do. But with y, it's different. So first you just take the derivative of y squared. It would be 2y. But then you have to multiply it by dy dx, because there's nothing that cancels out the x in the denominator. There's just a y on top, so you're stuck with that dy dx, because that's what the terms are. And then you take the derivative of the 1 on the other side of the equation, and it's a constant, so the derivative's just going to be 0. So this dy dx is very important in implicit differentiation, and your ultimate goal is to get it isolated on one side. So you subtract the 2x, and then you divide away the 2y, so then you get dy dx all on its own on the left side, and then the -2 divided by 2 cancels out, and you're left with dy dx equals -x over y. Okay, so here we have a more complicated example of implicit differentiation. X squared plus 2xy plus y squared equals 9. So x squared is easy, that just becomes 2x, and we know 9 goes to 0 because it's a constant. Now 2xy is a little more challenging because you have to use product rule. Beth split it up into 2x times y. So you take the derivative of the 2x first and multiply it by just y. So the derivative of 2x is 2, and so you get a 2y there. And then you add it to the derivative of y times 2x. 2x remains the same. The derivative of y is just 1 times dy dx. And then lastly, we have a y squared. So we add a 2y times dy dx. Don't forget that dy dx is very important. Equals 0. And then like I said before, we want to isolate that dy dx. So first thing Beth does, she subtracts 2x and 2y onto the other side, and then you can factor out the dy dx so that we can divide the whole thing by 2x plus 2y. And our final answer is dy dx equals negative 2x minus 2y over 2x plus 2y. And that's our answer.